Hi, everyone. We're going to start section 7.4 on partial fractions. And this will eventually involve systems, in case you're wondering what this is doing in chapter 7. Well, what are these things? What are partial fractions? You're going to get to know these very well in Calculus 2, Math 151, because you're going to have a section on integration by partial fractions. So you will see this in your Calc 2 class. Okay, let's start with a review example. So in the beginning, in your old school algebra class, you might have taken these two rational expressions and subtracted them. 3 over x minus 4 minus 2 over x plus 1. Your first step would be to find an LCD, a least or lowest common denominator. Here, since these guys have nothing much in common besides plus minus 1, we take their product. Just like if we had 1/2 minus 1/3, we would take the product of the denominators. 2 times 3, or 6, is our LCD. Now, as we build up the fractions so that we get this common denominator, right, we can take this first fraction and build it up. And to do that, we ask, who's missing? Who's missing from this denominator as we form the LCD? Well, the x plus 1 is missing. So why don't we multiply the top and the bottom by x plus 1? The fraction bar already groups the top and the bottom, but for good measure, we can do this. Maybe this too, right? And then, to build up this fraction, right, I'll put an arrow here. Who's missing from this bottom? Well, the x minus 4. So we'd multiply this fraction by x minus 4 over itself. Again, optional grouping symbols, but they're nice to see. So when you multiply these guys together and multiply these guys together, you get a common denominator, and you subtract these numerators. 3 times the quantity x plus 1 minus 2 times the quantity x minus 4. Again, one shortcut is to just write the LCD down here, and then for the tops, the numerators, you attach who's missing. For this fraction, x plus 1 was missing in the denominator, so he's part of the buildup when you build that fraction up. Here, x minus 4 is missing in the bottom, so you put the x minus 4 up here as part of that buildup. Think who's missing when you think about the pieces that have to be attached to these tops. All right, and then you distribute on top, combine like terms. When you subtract these rational expressions, you get this over here. X plus 11 over x squared minus 3x minus 4. So back in your algebra classes, you may have done that. Subtract these rational expressions and get this uglier looking guy down here. We're now going to do the inverse problem. What do I mean by that? The inverse problem. I give you something like this, and your task now is to break this guy up into a sum or difference of smaller, nicer fractions. So we go in reverse. I give you this ugly fraction, you decompose it into a sum or difference of nice partial fractions, which will be easier to integrate. And in calculus, you integrate term by term. So this is helpful. These guys you can integrate pretty easily, but you had to break this guy up first. Now, your ability to break this up into a sum or difference of partial fractions, that's going to depend on your ability to factor this denominator over the reals. So make sure you remember how to factor. And it turns out that there's going to be one unique way you can decompose this as a sum or difference of the kinds of partial fractions we're looking for, although you can switch the order. So again, the PFD form. How do we reverse this process? What we're talking about here is called a PFD, not PDF, like a file on a computer, not PDF, PFD, partial fraction decomposition. The PFD for this uglier fraction is this over here. We're decomposing this, we're breaking this up into a sum and or difference of these nicer partial fractions. The PFD form that we need will depend on the factored form of the denominator. So I know that once I factor this guy, I'm going to need a number over x minus 4 plus or minus a number over x plus 1. So once we know how to factor the denominator, we should be able to figure out the PFD form. And in fact, that's going to be problem 1 in your homework for this section. It's important that you know how to figure out the PFD form, because if you can't figure this out, then you're going to be dead if you have to do more, if you have to actually figure out the PFD over here. You have to know how to work out the PFD form. What form will this decomposition take? Okay, so I'm going to go straight to an example here. If we factor a polynomial with real coefficients over the reals, what potential cast of characters might we be looking at? Now, of course, on homework and exams, I would never ask you to factor a monster like this thing. But in principle, how does this thing factor, and what is the anatomy of the factorization? How bad could the factorization get? What are the potential pieces when you factor this kind of polynomial over the reals? All right. It turns out that this hideous polynomial ends up factoring like this. And I want to talk about the cast of characters here. If you factor a polynomial with real coefficients over the reals, what could be your cast of characters? And we're going to go through these one by one. And once we understand what these factors are like, once we categorize these factors, then we can talk about the PFD form that we're going to develop. And then later on, how can we actually get the PFD? All right. The cast of characters. So here's what I'll do. I'll leave this up here, and I'll make a copy. All right. And we'll talk about the cast of characters. Okay, first up. The 3 here is a constant factor. Sure, your final factorization could have a constant factor, like 2, 3, 4, and so forth. It could be 1, in which case you don't need a number out here. X squared is actually surprisingly tricky, and we're going to deal with that later on. We'll discuss x squared last. Surprisingly, he's the trickiest one to categorize. X minus 3, what do you call a first degree polynomial? You call it linear. And it's a distinct linear factor in the sense that there's no exponent here. We don't have copies. We don't have a square or a cube up here, for example. We don't have copies. We just have this distinct linear factor. It's all alone. Oh, and by the way, if you see 2x minus 6, make sure you factor out a 2 first. Okay, make sure you don't have copies in disguise. 2x plus 1, well, that's also a distinct linear factor. It's just not monic. There's actually a number in front of the x besides 1. But both the x minus 3 and the 2x plus 1 are distinct linear factors. There are no exponents on the top here. And they're both first degree. Now the square of x plus 4, see here we have 2 copies of x plus 4. So we don't have distinct linear factors over here. For the square of x plus 4, we have a nice power of a linear factor, like a square or a cube of a linear factor. And we can think of this as x plus 4 times itself. So we can think of the square of x plus 4, the cube of x plus 4, and so forth as a case of repeated linear factors. X squared plus 1. That's not linear, and we cannot factor it further over the reals. It's prime. So we're going to call x squared plus 1 a distinct R irreducible quadratic factor. Or in other words, it's a distinct quadratic factor that's prime over the reals. This sounds very technical. prime over the reals. All right. It's a distinct quadratic factor that's prime over the reals. It's distinct because we don't have a square or a cube on top of here, for example. All right. It's prime over the reals because this cannot be factored further over the reals. In the case of a quadratic, you can tell if a quadratic with real coefficients can be factored over the reals, depending on whether or not this has real zeros. If this has real zeros, we can factor this further over the reals. But x squared plus 1 has no real zeros. So we cannot factor this further over the reals. Finally, the cube of x squared plus 4. This time we have the power of a quadratic that's prime over the reals. Or we have repeated factors of that type. The cube of x squared plus 4 is a nice power of an R irreducible quadratic factor, or a quadratic factor that's prime over the reals. And because this can be rewritten as 3 copies of x squared plus 4 all multiplied together, we can think of this as an example of repeated quadratic factors that are prime over the reals. Finally, what is the deal with x squared? You might think, oh, that's quadratic. But the thing is, it has real zeros, right? Namely, 0 and 0. X squared can be thought of as, well, if you were to ask an algebra student, or if an algebra student asks you, what is x squared? You might say x times x, right? X times itself. X squared is not prime over the reals. X squared actually represents repeated linear factors because it can be written as x times x. In that sense, it's not prime. You can write x squared as x times x. You could think of this as the square of x minus 0 if you want to stress the fact that we have repeated linear factors. X squared, repeated linear factors. Think of it as x times x. It's not prime because 0 is a 0 of this quadratic. Again, we do not consider x squared to be R irreducible or prime over the reals because it has a real 0 or root, namely 0 itself. You can think of x squared as this, the square of x minus 0. So we've seen our cast of characters. Once again, what are these? A constant factor times, what are these? Repeated linears, distinct linear, repeated linears, a quadratic factor, prime over the reals, and powers of those. Repeated quadratics that are prime over the reals. Oops. Again, let's type these out. 3 is a constant. Three is a constant. X squared, again, surprise. Repeated linear. It's x times x. X minus 3, that's going to be a distinct linear. Same with this guy here, distinct linear. The square of x plus 4, again, repeated linear. So the square of x plus 4 was like x squared. X squared plus 1, once again, it's a quadratic that's prime over the reals. And here we have repeated repetitions of such factors. Repeated quadratic prime factors. Repeated quadratic prime factors over the reals. All right, our cast of characters for that hideous polynomial. But once you factor a polynomial completely over the reals, and you might get any number of these guys here, you can then figure out the PFD form. All right. By the way, if it's improper, if the degree of the top is not less than the degree of the bottom, we'll end up having to do long division. All right. If the rational expression is improper, okay, We'll have to do long division. We'll talk about that later. Now, my general comments here about PFD forms, they're textbook-like, good bedtime reading, perhaps. I'm going to go straight to the example. All right. Find the PFD form for this over here. It's a bit too involved for us to find the actual PFD, but let's find the PFD form. And what do I even mean by that? Okay. It means that we don't have to solve for the unknowns. All right. Here's the idea. What are these guys? X squared is what? Repeated linears. This guy here is what? The square of x minus 4. Also, repeated linears. What's x squared plus 1? It's not linear, and we cannot factor this over the reals. It's a quadratic with no real zeros. This is a quadratic that's prime over the reals. All right. So again, the cast of characters. X squared, repeated linear factors. Same for the square of x minus 4, but x squared plus 1. It's not linear, cannot be factored further over the reals. It's going to be quadratic, that's prime over the reals. All right, repeated linears. It turns out that these various factors will correspond to various partial fractions over here, or forms for partial fractions. Because we have an x squared in the denominator, we're going to run up to the power. What do I mean by run up to the power? We write x and then x squared. Because of the x squared, we have a fraction, a partial fraction with x in the bottom, and another partial fraction with x squared in the bottom. If we had x cubed here, we'd have another fraction, like plus c over x cubed. A, B, C, and so forth are going to represent real numbers that are unknown at this time. But from the x squared as a factor on the bottom, we get a over x plus b over x squared. These are the partial fractions we get from the x squared. Don't forget to put the plus sign there. Even though eventually b could be negative, that is possible. All right, now in blue, we have the square of x minus 4. Again, we run up to the power. We have x minus 4 all to the first, and then x minus 4 all to the second. If that were cubed, we'd have another fraction with x minus 4 all cubed down below. And again, we have constant forms on front. Remember, A, B, C, and D are all going to represent real numbers. We just don't know them yet, what their values are. Finally, in green, x squared plus 1, our quadratic that's prime over the reals, x squared plus 1. Because of that, we get this guy here. We copy him down below, x squared plus 1, but be prepared for a linear form on top. Not just constant. We could have something as bad as a linear form up on top. What do I mean by linear form? Think slope-intercept form. What was slope-intercept form? Slope-intercept form was y equals mx plus b. Well, similarly here we have ex plus f. You have your choice of letters, but of course don't use x again, and make sure that you don't get any copies. A, B, C, D, E, F, where these represent real numbers, we just don't know them yet. And it's almost like a combination lock on a locker. There's only one sextuple. There's only one sequence of 6 real numbers for A through F that will unlock this thing and will make this whole thing equivalent to this fraction over here. Oh, by the way, and if there's a square over here, you'd have another fraction. If you had a square there, in fact, I'll put it in. If you had a square here, put this in brown. If you have a square here, then you would have another, kind of hard to see. How about a bright purple? Okay, if we have a square here, all right, then we get another partial fraction. Again, we run up to the power. We have x squared plus 1 all squared in the bottom, we run up to that power. And on top, we have another linear form. What would you use? Linear form. Think slope-intercept form. You could use gx plus h, where g and h represent real numbers, but they're unknown. Here's the PFD form. So at this point, you can go up through 7.4 number 1 on the homework that deals with PFD forms. For a problem like this, I would not ask you for the values of a through f, or certainly a through h on an exam. That would be too involved. But the form is fair. I can ask you, what's the PFD form for this big ugly fraction over here? The PFD form is fair, but I would not consider the PFD fair. We have 6 unknowns here. I would not give you a problem where I would require more than 4. All right, later on, we're going to get more practice with these forms, and also how do we find the actual values for A, B, C, and so forth. So what is, in a way, the combination that would work, really the sequence of numbers that would work to unlock this whole thing? That's later on.